All right, welcome everybody. In this video, we are going to walk through how we can do a hypothesis test for a difference in two proportions using the central limit theorem as a way of constructing an approximation for the null distribution. So the example that we'll take a look at is, let's say we want to test a possible new medication to see whether it's more effective at preventing a disease from a current treatment or maybe just a control. So for example, let's consider an artificial sweetener xylitol, which we're curious to see whether xylitol is effective at reducing ear infections in children compared to no treatment at all. So in this case, the explanatory or predicted variable might be is the type of medication. And so there are two treatment groups. Either a child is placed into the treatment group, they receive xylitol, or into a control group and they receive a placebo. And the response variable here is whether or not the child gets an ear infection. So both of these variables, the predictor and response variable, are categorical. So here's where we can set up a test using a difference in two proportions. So here I'm going to let P of X and P of C denote the proportion of all children that receive xylitol or a control placebo that get an ear infection. So these are population parameters. And we don't have access to these since we're not able to perform this experiment on all possible children. So our claims in the null and the alternative hypothesis are about these population parameters. So our null hypothesis here would be xylitol has no effect on ear infections in children. So these proportions Px and Pc are equal to each other. Or in other words, the difference in these two proportions is equal to 0. And the alternative here is we are testing the claim that xylitol reduces ear infections in children. So this is a one-sided hypothesis test. So we think that Px is going to be less than P sub C. So in other words, we think that this difference, P sub X minus P sub C, is going to be less than 0. So let's see how we can go ahead and perform this hypothesis test, where now we're going to construct the null distribution to see just how extreme a test statistic is. Constructing this null distribution using the central limit theorem as a way of looking at the distribution of possible differences in sample proportions. So here, again, we're doing a test on two proportions. And so we would use a test statistic. We would perform an experiment. We would collect some data from a sample of children that receive xylitol, and we could calculate what proportion of those children get ear infection. And then we could collect data from a sample of children that get a placebo and look at what proportion of those children get an ear infection. And our test statistic would be, well, how significant is the difference in those two sample proportions? So the central limit theorem gives us a way of describing the distribution of sample proportions, the difference in two sample proportions. And we could use that distribution to look at a standardized distribution for the difference in two sample proportions. So in general, the way that we look at these standardized test statistics is we look at our observed difference in sample statistics. In this case, that would be the difference in two sample proportions. We compare that to the difference in the null claim. In this case, our null claim is that there is no difference in these two proportions, so that P1 minus P2 is 0. The difference in our sample proportions is not going to be 0. So we're going to have some difference. And then the question is, well, is our observed difference significant, or is that difference within the realm, in the margin of error that we can expect just from the randomness in sampling. And that's where the standard error from the null distribution comes in handy. And so then we could take a look at that difference in the observed difference in our sample proportions relative to the standard error of the null distribution. So we can use the central limit theorem to approximate the standard error for the null distribution for the distribution in the difference in two sample proportions. And so the central limit theorem for a difference in two proportions, it tells us that if we are picking from a population that population 1 has proportion P1, population 2 has a proportion P2, then, and we want to look at, I pick a sample from population 1 and calculate its sample proportion. I pick a sample from population 2, calculate its sample proportion, and then I want to describe the distribution of sample statistics P hat 1 minus P hat 2. Well, that distribution is going to be centered at the difference in the population proportion. So it's going to be centered at P1 minus P2. And the standard error we can calculate by taking the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. So we took a look at this a little while back. So we can use this description for the distribution of sample proportions as a way of looking at, well, how significant is our observed difference in sample proportions. But we have a little bit of an issue here in that, okay, we want to describe the null distribution. So the null distribution is set up under the assumption that the null hypothesis is true. And so our null hypothesis claims that P1 minus P2 is equal to 0, or in other words, that P1 is equal to P2. So our distribution P hat 1 minus P hat 2, we know it's going to be centered at 0 because, again, our assumption is that P1 and P2 are equal to each other. So we know where it's going to be centered. We know that in the numerator, when we calculate the standardized test statistic, we take our difference in sample proportions and we're going to subtract 0 from that because, again, that's the center of our null distribution. The question is, well, what is the standard error? And we can't really use our assumption in the null hypothesis to help us calculate the standard error, since our null hypothesis doesn't claim anything individually about P1 or P2. So in order to calculate the standard error for this distribution, I would need to know what is the value for P1, what is the value for P2. And we haven't claimed anything about those values. The only thing that we've claimed is that those values are equal to each other. So the question is, well, what would be reasonable values to use to approximate P1 and P2 in order to come up with a standardized test statistic to perform this test? So the null hypothesis is stating that there is no difference between these two populations. So the fact that some of these children, in this case, received the treatment, received this sweetener xylitol, and some of these children received the placebo, well, that didn't make any difference in terms of whether or not they got an ear infection. So according to our null hypothesis, we might as well just have grouped all of these children together in terms of their likelihood of getting an ear infection is concerned. So one reasonable thing that we can do, well, first of all, is our null hypothesis claims that P1 and P2 are equal to each other. So when we calculate the standard error, we should use the same value for P1 and P2. Okay, so what values should we use for P1 and P2? Well, we're going to assume again that these two populations, children that get xylitol, children that get a control, they're no different from each other. So let's just group them all together in one big group of children. And let's calculate, well, what proportion out of all children, regardless of which group they were in, treatment or control, what proportion of all of these children got an ear infection? We'll call this the sample pooled proportion. And let's use that as our estimate for both P1 and P2. So now we're going to use the same estimate for P1 and P2 when we calculate the standard error for this distribution of sample difference in two sample proportions. So the estimate for P1 and P2 is going to be this pooled sample proportion that we're going to get by grouping together. X1 would be the total number of successes. So in this case, a success might be a bad thing, such as the children from the first sample that got an ear infection. And then we're going to add to that all of the children from the other sample that got an ear infection. And then we're going to divide by the total number of children in our first sample plus the total number of children in our second sample. So we're going to add up together, we're going to pool together what were the total number of successes, X1 plus X2, divided by the total number in our pooled samples together, N1 plus N2. And that's what we're going to use for both P1 and P2 when we estimate the value for the standard error in our null distribution. So once we've got that component down, we can now come up with a standardized test statistic. And when we're working with a difference in two sample proportions, the central limit theorem says that that distribution is going to be approximately normal distribution as long as our samples are large enough. And so at the end of this notebook, there's a little summary about how large do samples need to be when we're doing different hypothesis tests, when we're using the central limit theorem for different statistics. So if we assume that our samples are large enough, then we're going to use a normal distribution. So we're going to calculate the z-score for our observed test statistic. So in this case, we would take our test statistic, which would be the difference in sample proportions. We're going to subtract that from the claim in our null hypothesis, which is that this difference would be 0. And then we're going to divide all of that by our estimate for the standard error of the null distribution. And so now we're going to replace the P1 and the P2 in that previous formula with the pooled sample proportion. And so that previous formula is going to, once I substitute this pooled sample proportion into that formula, it's equivalent to the formula that I've typed here, which is the square root of the pooled sample proportion times 1 minus the pooled sample proportion, all times 1 over N1 plus 1 over N2. And so that's how we can calculate our standardized test statistic. And again, this is just using the central limit theorem for a difference in two sample proportions. And we're just replacing P1 and P2 in that formula with the same value that we get by pooling our two samples together and calculating the sample pooled proportion, which is the formula given up here above. Okay, and then once we've got our standardized test statistic, we can go ahead and calculate the p-value the same way that we've been doing things before. So for example, if we're doing a one-tailed, left-tailed test, we calculate our standardized test statistic, and then we can use the p-norm function to calculate the area to the left of that standardized test statistic. If instead we had a right-tailed test, we can calculate that standardized test statistic, and then we want to calculate the area to the right of that. So we would do something like 1 minus p norm. If we're working in R, we would do 1 minus p norm z01. And if we're doing a two-tailed test, then we could calculate the area in one of those tails and multiply that by 2, for example. Okay, so let's take a look at some data relating to this example with xylitol. So let's say this is based on a study that was done. And so in that study, there were 165 children that took a placebo and 68 of the children in the control group that got the placebo got an ear infection. And there were 159 children in the treatment group that got xylitol. 46 of them got an ear infection. And so let's say we're going to perform this test using a 1% significance level. So we've stated our hypotheses earlier. And so the first thing we want to do is we want to calculate the standardized test statistic. So the first thing in order to do that is let's calculate the standard error for this null distribution. And again, this null distribution is going to be for the difference in two sample proportions. And what that would look like down below is we would calculate our pooled sample proportion. And that pooled sample proportion, which is the 0.3519, I have these calculations down here in this R code cell below, is we would take the 68 children that got an ear infection in the control group. We would add to it the 46 children that got an ear infection in the treatment group. So that's the total number of children that got an ear infection altogether, pooled together. And we would divide that by the total number of children in the placebo group, the 165, plus the total number of children, the 159 children in the treatment group that got xylitol. So in other words, we're taking, if we pooled these two groups together, all of the children that got an ear infection out of all of the children that were in this study. And that's our pooled proportion, and that's this 0.3519. So I take the 0.3519 times 1 minus the pooled proportion, all times 1 over 165, the number of children in the control group, plus 1 over 159, the number of children in the treatment group. And that comes out to approximately 0.0531, which is the standard error for this null distribution. And you just want to be really careful about how you enter these formulas into a calculator or R, that you're using your parentheses carefully. So right here, these parentheses go around the entire sum of 1 over 165 plus 1 over 159. So I've entered that carefully down here in this R code cell. The output is telling me the pooled proportion as well as the standard error for this null distribution. Okay, and so part B is asking us to find the z-score of the observed difference in sample proportions. So I'm going to need to use this standard error in order to find that z-score. So the first thing we would do is calculate the non-standardized test statistic. So I've got a sample proportion for those children that were in the control group that got the placebo, what proportion of them got an ear infection. So that's what P dot control is. Next, I would calculate the sample proportion of the children in the treatment group that got xylitol, what proportion of them got an ear infection. And then I would take the difference, and consistent with how I stated my hypotheses. So when I stated my hypotheses, I did P sub X minus P sub C. So I'm going to calculate my test statistic similar to how I ordered my difference in my hypotheses. So I'm going to do treatment proportion minus control proportion. And so here you can see that about 29% of the children in the treatment group got an ear infection, compared to about 41% of the children in the control group. So that's a difference in about 12%. So this is telling me that the children that got xylitol, they were about 12 percentage points less likely to get an ear infection than the children that got a placebo. So that seems like a big difference, but maybe that difference is just due to the randomness in sampling. So this is where standardizing this difference is useful. So if we divide that difference by the standard error, this is going to tell us, well, how many standard errors from the null claim is this difference? So I'm going to take my observed difference and divide it by the standard error. And this gives me a z-score of minus 2.314. So this tells me that our observed difference in sample proportions, this is like 2.3 standard errors below the null claim. And so now we can see, well, that's pretty far away. Whenever you get more than 2 standard errors away from the center of a normal distribution, that difference is usually pretty significantly far away. And so based on the standardized test statistic, we were looking at a one-tailed test. We had a left-tailed test. Our hypotheses were that our alternative hypothesis was that P sub X minus P sub C was less than 0. We were testing the claim that xylitol was going to reduce the incidence of childhood ear infections. So here, our p-value is just going to be the area in the tail to the left below our standardized test statistic. So we could do p-norm z dot ear, that was the z-score of our test statistic, 0, 1. And this gives us a p-value of 0.0329. Another way that we could have done this was using the prop test function, where I enter as a vector our two x values, the number of children that got an ear infection in the treatment group, a number of children that got an ear infection in the control group, followed by the 2 sample sizes, what our alternative hypothesis was. So here we had a one-sided left tail test. And here, whether or not we want to apply a continuity correction, we'll talk about how we can apply this in class together. For now, we won't apply the continuity correction. And you can see down here, we're getting a p-value, which is consistent with the p-value that we got doing this by hand. And so we got a p-value of 0.0103. If we are doing this test, way back at the start, we said we want to choose, here we're making a medical decision here. So we chose a small significance level of 1%. Our p-value is just barely above that significance level of 1%. So if we choose a 1% significance level, this result, although it seemed fairly unlikely, is actually not unlikely enough. So our p-value is not smaller than the 1% significance level. So this would be not statistically significant for that 1% significance level. Our test result here would be inconclusive, and we actually would not be able to claim with any level of certainty whether or not xylitol has any effect on reducing the incidence of childhood ear infections at this 1% significance level. Okay, well, that is a wrap. There is an appendix at the end that kind of gives a little bit of a summary overall of hypothesis testing, as well as how large sample sizes need to be if we're going to use parametric methods for different types of hypothesis tests. And we'll talk more about doing hypothesis tests for differences in 2 proportions in class together. Okay, thanks, everybody.